This time, we are going to talk about linear transformation with domain and codomains of different dimensions. We have here the first linear transformation from R2 to R3, and our second linear transformation from R3 to R2. And still, this is on the standard matrix for the composition of a linear transformation. So we have already shown in the previous video that the composition for linear transformation does not necessarily have commutativity, just like in our composition of functions. So we really need to show and use proper operations when dealing with them. This is the first composition of linear transformation T, represented by the composition of T sub 2 and T sub 1. In other forms, you could also rewrite it this way. Of course, no need to be stressed with this, just a show of the equivalent forms. And for T prime, this linear transformation, if we are going to interchange T sub 1 and T sub 2. Again, they don't necessarily have the same result. Here we are going to show their standard matrices. The standard matrix for our composition T is just equal to A, while for our T prime, let's coin it A prime. And the result for the standard matrix of our A is the product of A sub 2 and A sub 1 matrices, while this is prime, not inverse. We will have inverse a little bit later. It's just prime. For A prime, it's A sub 1 and A sub 2 matrices. But where do we get this A sub 1 and A sub 2 matrices? We're going to take them out from the results of our linear transformations respectively. For A sub 1, we're going to take it from the linear transformation T sub 1. This would be in a matrix form, okay, where take note that what they call this one, it should be an element of domain. So R2, okay? In short, there should be two columns here. And the two columns are indicated by the values of x and y. So the first column would be for the x, the second column for the y. And where do we get that? From each of these entries here. We know that this should have two columns, and then we'll start with the first, negative x, so that's negative 1, and plus 2y, that's your second entry here, 2. Next, x plus y, that's 1x plus 1y, and finally x minus y, so you have 1x minus y. Notice again, we have two columns as this is an element of our domain here. For A sub 2, since our domain is R3, so we're expecting here to have three columns indicated by x, y, and z. X for the first column, y for the second column, and z for the third column. And the entries will be dependent on this. X minus 3y, so x, that's 1, minus 3y. And again, we are expecting to have three columns, and since there's no z here, simply use 0 for that. Second entry here is z. You know that z, even if it's written first here, it should be in the third column. So you have z, you have 3x, and you don't have y. These are your two matrices here. Okay? Now for our first standard matrix, for our first composition, which is denoted by T, is the product of A sub 2, which is 1, negative 3, 0, 3, 0, 1, and our A sub 1, which is negative 1, 2, 1, 1, 1, negative 3. Notice that the first matrix is a 2 by 3 matrix, and this is a 3 by 2 matrix. The product is defined, and we are expected to have a result, which is a 2 by 2 matrix. Okay, that's the result here. So let's show that 2 by 2 matrix by multiplying the corresponding entries. 1 times negative 1 is negative 1. Negative 3 times 1, negative 3. 0 times 1, 0. Negative 1 plus negative 3 plus 0, negative 4. Next, 1 times 2 is 2. Negative 3 times 1 is negative 3. 0 times 1 is 0. 2 plus negative 3 plus 0, that's negative 1. Okay? Next would be 3 times 1, negative 1 is negative 3. 0 times 1 is 0. 1 times 1 is 1. We have negative 3 plus 0 plus 1, you have negative 2. And finally, 3 times 2 is 6. 0 times 1 is 0. 1 times negative 1 is negative 1. 6 plus 0 plus negative 1, positive 5. See, your result here is a 2 by 2 matrix. That's correct already. Now for A prime, this is a product of A sub 1, which is a 3 by 2 matrix, negative 1, 2, 1, 1, 1, negative 1, times a 2 by 3 matrix, 1, negative 3, 0, 3, 0, and then 1. Take note, this is a 3 by 2 matrix, 2 by 3 matrix. The product is defined and it should be a 3 by 3 matrix. As mentioned, there's commutativity is not all the time true for multiplication of matrices. Take note, we have a 2 by 2 matrix here, and we are expecting to have a 3 by 3 matrix for A prime. That's why it's really a proof that there's no commutativity for multiplication matrices. At the same time, the composition of linear transformations. So we have here the product. So this is 3 by 3, 3 by 3. Let's start. Negative 1 times 1 is negative 1. 2 times 3 is 6. Negative 1 plus 6, that's positive 5. Next, negative 1 times negative 3 is positive 3. 2 times 0 is 0. Positive 3 plus 0, that's 3. Next, negative 1 times 0 is 0. 2 times 1 is 2. 0 plus 2, 2. Next, 1 times 1 is 1. 1 times 3 is 3. 1 plus 3, 4. 1 times negative 3 is negative 3. 1 times 0 is 0. Negative 3 plus 0, negative 3. 1 times 0 is 0. 1 times 1 is 1. 0 plus 1, 1. For the last row, 1 times 1 is 1. Negative 1 times 3 is negative 3. 1 plus negative 3, negative 2. 1 times negative 3 is negative 3. Negative 1 times 0 is 0. Negative 3 plus 0, negative 3. And lastly, 1 times 0 is 0. Negative 1 times 1 is negative 1. 0 plus negative 1, negative 1. This is the result. This is a standard matrix for the second linear transformation denoted by T prime. It's a 3 by 3 matrix. So they are not the same as of the first. Again, this is how we show the standard matrix for a composition of a linear transformations where the domain and codomain are not of the same dimension. Thank you very much for watching.